What's up, guys? It's Dr. Tim Jackson with another episode of the Boss Body podcast. Brain health, neurological conditions, cognitive decline. If you haven't experienced it yourself, you probably have a loved one or a colleague or friend who has. So I brought in a subject matter expert, the man, the myth, the legend, Dr. Dayan Goodenowe.
While I make every effort to broadcast correct information, I'm also still learning. I will double check all my facts, but realize that healthcare is a constantly changing science and art. One doctor or healthcare provider may have a different way of doing things from another. I welcome any comments, suggestions, or correction of errors. I take no money from supplement or device companies. By listening to this podcast or reading this blog, you agree not to use this podcast or blog as medical advice or to treat any medical condition in either yourself or others, including but not limited to patients that you are treating. Consult your healthcare provider for any medical issues that you may be having. This entire disclaimer also applies to any guests or contributors to the podcast or the website. Under no circumstances shall any guests or contributors to the podcast or blog or any employees, associates, or affiliates of the Boss Body podcast be responsible for damages arising from use of the podcast or the blog. This blog or podcast should not be used in any legal capacity whatsoever, including but not limited to establishing the standard of care in a legal sense or as a basis for expert witness testimony. No guarantee is given regarding the accuracy of any statements or opinions made on the podcast or the blog.
Well, thanks for being here. Thanks for taking the time out of your schedule. So I first came across your work, I think like 3 years ago, but then I really started following it about 2.5 years ago. And so tell us about what a prodrome is and why is it clinically significant?
Yeah, so I've been in this for a long time. So my background in the psychiatric research at the biochemical mechanisms of neurological disease spans from the early 90s. And when I was developing technology, the ion cyclotron mass spectrometry, which allows us to measure thousands of small molecules simultaneously in the blood sample. And this was technology developed for diagnostic purposes, saying, hey, you know what? If we see someone with an illness, there's got to be a biochemical correlate of that illness in their blood or a tissue sample. And we did a lot of work in animal models, cell culture models, and so on. But we applied this to clinical research, and we did lots of large longitudinal clinical trials with the anticipation that, for colon cancer or dementia, we'd find these biomarkers that were related to the disease. So we think, hey, if someone has a disease, this disease is actually going to be causing these biomarker changes, right? So we're looking for, it's a medical biotech company, and we're looking for biomarkers. And the fact is, yes, we found them. So there's clearly, if you can visually see a disease in front of you, there is a biochemical correlate of that disease. That's pretty diagnostic. And this technology was very, very powerful at doing that. And the real eye-opening experience for me was actually in colon cancer. So we developed these biomarkers for colon cancer, which is very accurate for early stage colon cancer, assuming that we were measuring the effect of a tumor on human biochemistry. So we did this big study in Osaka, Japan, where we looked at individuals prior to surgical removal of tumors and after surgical removal of tumors, expecting that these biomarkers go down in the blood, right? So they're deficiencies that are diagnostic of colon cancer. And they're really powerful. We did like a 6,000 person clinical trial on colon cancer screening, and it gave us 87% sensitivity for stage 1 colon cancer. So pretty amazing. Anyway, so we did this expecting, okay, because we're so, we're smart scientists, we think we can predict everything. So we do the study, expecting that after the tumors have been removed and the individual has been given essentially a clean bill of health from a cancer perspective, that these biomarkers would come back to normal. Well, it turned out it didn't do anything to the biomarkers. So the biomarker was the same before the cancer surgery as they were after. So we said, but this doesn't make any sense. Like, what's going on here? So didn't even believe it. So we redid the entire study over again with a different university in Chiba University, Japan. Got exactly the same results. And that's when it really started hitting me that we are biochemically speaking, that there are biochemical changes that occur prior to a disease. there's basically, it's the bald tire analogy of biochemistry, right? There's a bald tire versus a flat tire. And these prodromes are essentially bald tires. And they're predictive of a future flat tire, but you don't know exactly when it's going to happen because you still need an environmental insult. You still need that nail, right? Like you can drive on a bald tire for a long time and not get flat. And so, but the odds are against you, so to speak. And, you know, and we see this all the time with these rare diseases. And we have a big program with ALS, for example, amyotrophic lateral sclerosis, where people, there's a subset that have a genetic mutation that clearly gives them familial ALS. Scary, scary, scary disease. But what's interesting is that you don't know when the person gets the disease. Okay, so you could be born with a genetic risk factor for this disease, and you might get it when you're 30, you might get it when you're 40, you're most likely to get it around 60. And so there is a huge span of time in which you have this, clearly this prodrome, you have a risk. This genetic risk is providing some level of susceptibility, but yet you don't really know when it's going to happen. And these genetic risks, same thing with the ApoE4 genotype for Alzheimer's, all these genetic risks that we've tracked, they're actually biochemical risk factors because these genes have biochemical mechanisms. And so similar things happen with Alzheimer's disease and sarcopenia, like muscle wasting, you know, all these different diseases. So when we studied the complex biochemistry, it actually becomes less complex because, and we really, this prodromal concept of, hey, the system is designed to work. And what was really interesting about this process is that sometimes just the obvious kind of hits you in the side of the head every now and then. It's going, wow. You know, we do all these clinical research studies, right? We say, hey, let's compare someone with Parkinson's with someone with control, or we compare multiple sclerosis versus control. And we forget that in every single one of these studies, we have a control arm. So in fact, the most heavily studied human population is the control population, because there's always a control arm in every one of these trials. And then you start thinking of this as these prodromes as basically a deviation from health. And so you have this, and these deviation can be sometimes highly predictable, right? And so one of these molecules was these plasmalogen molecules, which was another really big surprise molecule. They're a lipid, they're part of your biological membranes. And we've known about them for years, right? The original plasmalogens were discovered, I think, in the early 1920s. And we realized how important they were for human health in the 70s, because there's these rare diseases in children, these peroxisomal diseases. And these plasmalogens are made in peroxisomes. And so we know we'll have lots of them, like 30% of your brain phospholipids are plasmalogens, like a big amount. 50% of your phospholipids in your heart, huge amounts of these molecules in the human body. And we did these studies with children that have, so there's these rare diseases that happen, right? People that have a genetic mutation in a particular enzyme or protein that prevents them from making a particular molecule. And so there's a few diseases that affect this plasmalogen manufacturing in the body. And it's devastating, right? These kids typically die by age 5. So it becomes very, very clear that, you know, your body needs plasmalogens. Like you can't, there's no backup plan, right? And we knew this stuff, but you know, there'd been some little studies here and there showing plasmalogens decreasing, you know, in MS or in dementia and postmortem studies. But everyone really thought it was due to oxidative stress, because these molecules are very potent anti-inflammatories. They're very potent antioxidants. And so they're assuming, okay, you know, as you get older, you get more oxidative stress. If this oxidative stress is going to, you know, eat up these plasmalogens. Thinking really the same way I was thinking earlier with the whole colon cancer program, was that the disease process was eating away at the plasmalogens. Thinking, oh, you know what, these amyloid plaques and these neurofibular tangles, they're actually chewing like Pac-Man on my plasmalogens.
Yeah.
And what turned out to be the case is not that. It's the other way around. These low plasmalogens were actually causing amyloid accumulation in the brain. And so it was actually our bodies, as we get older, or under certain stress situations, the amount of plasmalogens we make is insufficient for the bodily processes that we rely upon them on. And this became, so the next question obviously was, well, how do we replace these damn things, right? Like, it can't be that hard. Like, if it's that, if it's in all of our membranes, like, come on, like, you've got to be eating this stuff. Like, it's got to be in animal products, which it is. But by a strange twist of fate, these molecules have the very last step in their manufacture in the body creates this bond. It's called a vinyl ether bond, which gives them all their superpowers. But it also makes them extremely sensitive to acid. So it's actually what your body uses. It's the first line of attack on breaking down peroxides. So, and this is actually really interesting for athletes, that all these super athletes that have been like the prime human specimens, if you will, and so many of them age so poorly, is that you can burn them out, these peroxisomes. But anyway, so the point is that there is plasmalogens in our food supply, but they don't make it past your gut. They all get digested in your stomach. And the story gets more and more interesting as you take the string and you pull this plasmalogen story apart, and you start getting into early childhood development and even breastfeeding. So the question is how do you get these plasmalogens? What form of plasmalogens can be used to enhance or restore our natural human biosynthesis capacity? And it turns out it's these what's called alkylglycerols, or plasmalogen precursors. And one of the only places we find them is actually in human breast milk, which is very interesting because in this breastfeeding, especially in the first 6 months of life, correlates so strongly with brain development, early myelination of the brain. It correlates with reduced incidence of autism, which is fundamentally a white matter myelination disease of learning, and so, which is great when you're 3 months old. It's not so great when you're 50, because availability of breast milk kind of gets scarce when you get older.
Right.
And so the question is now, how do we actually do this in a real way? So I'd invented and patented these plasmalogen precursor molecules that could restore plasmalogens. And it's interesting because your body has different ones. We talk about performance. We're talking slightly before we went on camera here. And there's kind of two components of our neurological systems. And people focus on the neurological, the neurons, right? The firing part. But there's also the protective coating part. And so when we take a look at the human brain, we roughly separate it into gray matter and white matter, right? And so, and about 60% of your brain is white matter, and that's basically just insulation. Like that's plastic coating on wires, and that's a different type in your neurons and your periphery, like your Schwann cells, to give you fast connectivity, and all your performance really comes from the myelination process. That's actually, people think that it's all from the synaptic firing part, but really the strength and the quality of your myelination is what gives the strength of your neurological signals. And that's all white matter. And that's what the breast milk type plasmalogens provide. They're omega-9 plasmalogens. And then you have the gray matter, which is about 40% of our brain. And that's the neuromuscular junction and everything else that controls, even heart rate variability, right, is being controlled by that. And so that gray matter has a different type of plasmalogen. It's an omega-3 plasmalogen. And it's so, human biochemistry and physiology is so exciting because we have all this stuff in our normal world. Like, we take the high tech, we talk about iPhones, and we have these cars that can do amazing things. We can get to the moon, and we have all this electronic technology, and we forget how mind-boggling the human brain and physiology really is. Like, your neurons are firing at somewhere between a 50 to 100 hertz, which means that's 50 to 100 times per second. Your neurons are bursting and reforming on this membrane structure. And that's all driven by these omega-3 plasmalogens. And so as we get older, one of the core components of aging and dementia is this synaptic function, specifically in, not to get geeky, but one class of neurons, the acetylcholine neurons, that's what drives cognition. But it's also what drives your neuromuscular junction. So when you see cognitive decline, you'll see how closely cognitive decline typically correlates with reduced neuromuscular function and muscle wasting. And likewise, so people that are frailty is also highly associated with cognitive issues as well. So maintaining skeletal muscle mass, from all of us that are trying to maintain our health and be optimized, it's one of the biggest things that we need to be focused on because it drives our metabolism. So anyway, that's a very long, rambling story about prodromes. And so now it's really changed our thinking from chasing one disease after another. And so we have all this advanced technology. We have diagnostic technology. We use the last 100 years of really good, robust medical technology, but we look at it differently, right? Rather than trying to chase a disease and try to chase the symptoms of disease, we look at deviations from health. And we can use this information to say, you know what? There is an operating manual for the human body. Like there is the manufacturer's specifications. Like the body is supposed to operate in a certain way. And we can measure deviations from that. It's like measuring the oil in your car. I don't have to wait for the engine to seize and say, oh, I guess it's time to put oil in it. Like I can actually use a dipstick and say, you know what? I don't need, someone else has showed me that when the dipstick is low, something bad happens. I don't need to wait for that. Okay. I just need to say, if it's not where it's supposed to be, let's put it back to the specifications. And that's what our research has been working on. And then developing these simple tools. And it actually becomes, we actually have a lot of tools, like the nutrient, strategic molecules, the plasmalogen precursors are one. Phosphatidylcholine is another big one that we don't do very well. And people, there's a lot of, plant-based versions, but I've developed an egg yolk oil phosphatidylcholine, which is really critical because we aren't plants. And there is a very structural difference between the phosphatidylcholine that we get from plant products versus an egg or a liver or, a streaky pork, other animal sources of phosphatidylcholine, which is a critical part. And then,
so you're probably, sorry,
okay.
You're probably familiar with the Patricia Kane protocol.
Yeah, so the phosphatidylcholine is one of the molecules that we measure on our prodrome scan blood test very carefully and look at different structure, different types of phosphatidylcholine. It is one, along with plasmalogens, it should be measured in everybody's blood test all the time. It is one of the core determiners. See, we consider it a non-essential nutrient, okay? And this is, people don't realize where essential and non-essential came from. Essential nutrients like a vitamin C or a vitamin D, because we say, okay, if I'm completely deficient in vitamin D, I'll get rickets, right? If I'm completely deficient in vitamin C, I'll get scurvy. And so your body has an absolute demand of it because you can't make any of it in your body. Like 100% of it has to come from some source, right? And so we call those essential. And anything that your body can technically make, we call non-essential, even if it's really energetically demanding to make it. So choline, phosphatidylcholine, is technically called non-essential because your body can make phosphatidylcholine, but it's quite energetically demanding to do so. And it causes a lot of oxidative stress. It elevates homocysteine and a whole bunch of things. So it's very common to become deficient in it. And it really screws up a lot of things. Like virtually every single person who ever gets pancreatic cancer has a choline deficiency. Full stop, period. Okay, your cardiovascular system, your reverse cholesterol transport system is heavily dependent upon adequate choline levels. And so getting enough choline in our diets, and this is really tough for people that are doing, high vegetarian diets and things. You're just putting a lot of stress. Other than, there's a few core nutrients that we need to get from an animal source that our human body is designed for. Creatine, carnitine, some of your sulfur amino acids, they're quite deficient in plant. So if you are going to be a strict vegetarian, you really got to be up on your, core nutrients that you just can't get from plant sources in a reasonable way. And so you just need, so those are the kind of things that we do now. And so the phosphatidylcholine is a big deal. It's, if you have patients that have low HDL levels and chronically low HDL levels, phosphatidylcholine is usually a culprit. And the DHA plasmalogens are another big contributor to your cardiovascular cholesterol regulation system.
You need phosphatidylcholine to synthesize bile, and if you can't make bile, you can't detoxify. So, and then there's a polymorphism, you probably know, MTHFD1, where you're less likely to make sufficient amounts of phosphatidylcholine. So there's a number of things. And then I work with a lot of people with mold toxicity and stealth pathogens. And so you get those lipid rafts. And so by replenishing, the phosphatidylcholine, the cell membranes work better, which means the tissues and organ systems work better. So I know you mentioned omega-9s and omega-3s. So are plasmalogens converted from the omega-3 fatty acids and omega-9s into the alkyl glycerols, and then they're converted into the plasmalogens?
No, so the plasmalogen is a backbone itself. So most phospholipids are what's called a glycerol backbone. Okay, so they're little think of a power strip with 3 plugins, and you plug 3 things in. And on one of the positions is a polar head group. It's like phosphatidylcholine or ethanolamine or inositol or so on, serine. And then the other 2 positions are fatty acids. Okay, and that's where your omega-9s and omega-3s come in, right? The backbone itself is what determines whether it's a plasmalogen or not. And so the alkyl glycerol part is, and that's the critical component. The SN1 alkyl glycerol is made specifically in peroxisomes, and that's the part that makes it a plasmalogen. Then you can modify it. It can be an omega-9 plasmalogen or omega-3 plasmalogen. So the omega-9 and omega-3 refers to the type of fatty acid. That's on all types of phospholipids, but the plasmalogen deals with the actual backbone of it.
Okay.
And then your body uses different types of plasmalogens for different types of cells, right? So your oligodendrocytes and your Schwann cells that make your myelin, they use the omega-9 version, which is oleic acid. And then your synapses and your neurons, your reverse cholesterol transport system, like your endothelial layer, heavily dependent on the omega-3 plasmalogens, lung function, kidney function, neuromuscular function. Those are heavily driven by the omega-3, the DHA version but the plasmalogen backbone is the same across the different ones.
And so you have the glycerol backbone, correct?
Yep.
And then you have you said either omega-3 or omega-9.
Correct. Attached to.
Those were the 3 parts of the 3-prong system.
Exactly.
Okay.
Right.
Because I think it's been a while since I looked at your site, but and this gets into another topic I know you're passionate about, and so am I, but microglial cells, microglial activation, microglial priming. And so for the listeners, we've discussed it kind of peripherally, but if you have microglial activation short term, you're going to have brain fog, irritability, but long term, you get neurodegeneration, correct?
Correct. Yeah. So microglial activation is critically component of especially white matter damage in the brain. Okay, it really affects the myelination process. So basically all children with autism have microglial activation. Okay, it's an inflammatory, it's a disease that affects the white matter. Same thing with multiple sclerosis, it really affects the white matter. And anyone with post-COVID, those type of syndromes, especially in the brain is like a castle. Once something breaches the wall, it kind of gets stuck in there, and you kind of have to fight it from inside the wall. So microglial activation it's doing its job. That's the problem is the microglia isn't doing its job. It's actually doing its job. What stimulates microglia is a sick cell. Okay, microglia are these. It's your neighbor that says, "Get off my lawn." It's just annoying cells that are always looking for something to piss them off. That's what your microglia are, right? And so they're out there looking at the cells to see if there's anything unhealthy with the cell. And when they find an unhealthy cell, and typically the measure of a cell being unhealthy is the membrane gets peroxidated. Oxidative stress causes peroxidation of the membrane. And then that activates the microglia. And the microglia says, oh, here's a sick cell. I'm going to go attack the cell, and I'm going to get rid of the cell because my job is I want to kill that cell and have my macrophage around it to eat all the garbage from it, so you don't have sepsis, basically, at a cellular level. And that's what its job is to do. Now, when you have weakness, mitochondrial weakness in particular, that microglial activation, when it is activated against the target cell, which is a sick cell, and its job is to kill that cell and clean it up, the cells around that cell become damaged by the microglial activation. And this is what we call autoimmune. So autoimmune disease is really nothing more than mitochondrial insufficiency. So when you have a natural immune response to an event, then an immune system is activated and it attacks a cell. If the surrounding cells are not able to withstand the glia, the microglia attacking that cell, then they become oxidized themselves. And so then the forest fire just keeps on spreading. And then you end up with this chronic microglial activation. So children with autism, for example, if you take an autistic child at age 8 and the same person when they're 40, and you look at their brains, they pretty well have inflammation their entire life. And we have the same situation with concussion, like sports injuries. Like these are things that a lot of these inflammatory events in the brain, they just don't go away. Okay, your body kind of adapts around them, and they're kind of just hovering slowly. And so to get rid of them, you actually have to take a targeted approach. And the targeted approach really is boosting the mitochondrial function, okay, with core supplements, but the plasmalogens and restoring membrane structure and function. Because the membrane structure is actually what stimulates the microglia. If the membrane is not oxidized, the microglia go away. Okay, they're not going to be activated if you can. And so there's two parts of that. One is stop the cell from spitting out all these reactive oxygen species, and that comes from improving mitochondrial strength. And the big, we talk about B vitamins; those are all important, very important. Like your B1, they're B1, 2, and 3 for a reason, right? Thiamine, riboflavin, niacin. But then the big hammers too, people forget about just N-acetylcysteine and maintain the glutathione levels, acetyl L-carnitine, and CoQ10. Study after study shows that they reduce, volumes of stroke volumes, like for stroke issues. So, and then that in combination with a good lipid protocol, with the plasmalogens, and we use the egg yolk oil because that's what the brain needs. Like it needs an omega-9 phosphatidylcholine. And so there's the good news is that there's really black and white mathematical ways of dealing with these things. Like and tools are actually generally available. Most of them are reasonably, cost effective. Some of them are more expensive than others, for sure. But we have a lot of good tools in toolbox now for these situations, like people dealing with these inflammatory. We have dramatic results in autism children, like get this inflammation under control, or long COVID individuals, or autoimmune. And like I just did one of the roundtables on multiple sclerosis. One of my clients restored vision after 25 years of blindness. Okay, so she's blind for 25 years. She can now see out of one of her eyes again. And so the brain has the human body has incredible neurogenesis capabilities. If we feed it, if we just allow it to do its job, right? Like if we can, the different cells of your body, they're designed to do their work. Like an oligodendrocyte is designed to myelinate. Like if we can feed it the right, it will do its job if you let it. Okay, a cardiomyocyte in your heart, it will do its job if you let it. And so I think a lot of times what we have is we just don't know. We get deficient, we get underwater, and the body just can't catch up, right? And
Right.
part of our job is to restore that. And then the harder part sometimes is repairing whatever cumulative damage someone has suffered, right? That can be the longer process. So that's microglial activation of the brain is a big deal. It's a big deal, and there are tools that can dramatically improve it.
And so with things like vitamin E, I know that's extremely important for preventing lipid peroxidation. Can that be helpful as an adjunct?
I think vitamin E is important. It's the reason, like, clearly you don't want to be vitamin E deficient, but whether or not pumping a whole bunch more in, okay, like you want a moderate amount. Okay, the CoQ10 is something people get deficient of quickly, so that's a couple 100 milligrams of that. And what we're finding really in the brain, the plasmalogens really are that weak link. It really feels like because look, we've been doing this for years and years and years, trying to solve, like, these problems that we're talking about today aren't new ones. And everyone has tried so many different combinations of things. And we get kind of success here and success there. And we get this, it feels like you're at Vegas and you're just kind of hoping for 777s, right? And sometimes you do. Sometimes you hit that right combination, and that person walks away thinking, wow, my B12 deficiencies. Like, my goodness gracious, if you have a bad B12 deficiency and you get B12 in your system, you think your life has been miraculously overturned, right? Because it is, because if you do find that one deficiency, it can really work. But what we're finding is that this plasmalogen deficiency thing has been a major missing link, because we obviously use everything else in combination with it, but it's been that one bulky hammer that's been missing, because we've had no way of actually physically adding it. Like vitamin E, for example, right? Like you can physically add it. Phosphocholine, you can physically add more in, or N-acetylcysteine. I can give you that. I can restore the glutathione levels. Like these tools have been around, but restoring plasmalogen levels once they're deficient, we actually haven't had a tool for that until with these plasmalogen precursors. And since we've used them for the last few years, we've learned how important they are. But we're going into massive doses, and this is what's happening with ALS and multiple sclerosis, really changing neurogenesis and neuromuscular development. We're learning that this has been a critical missing link. We still do everything else that's important. Like I always tell people, there's both 3 or 4 really core systems that people stay focused on: mitochondrial health, and our prodrome scan blood test looks at mitochondrial leakage. It's a very simple test to see if it's burning properly. Your energy regulations, good old fashioned fasting triglycerides tells you a lot, making sure cholesterol levels are proper. So the mitochondrial function, the methyltransferase function, which is the choline system, homocysteine system. We look at sphingomyelins and ceramides. It also tells a story there. And then your membrane structure and function, like your phosphocholine and your plasmalogens. These are core structural things. If you can get those, if you can get those 3 things in your cholesterol regulation in place, like if your triglycerides are in that 60 to 90 range, you got your HDL levels in that 60 to 80 range, total cholesterol is over 200 and at 220, like your system is healthy. Okay, like you got some big things going on. You make sure your creatinine, like muscle wasting as we get older, people forget that. I can't tell you how many people we put on creatine, just good old fashioned creatine. Everyone over 50 should be on creatine. It's such a main driver of kidney and liver health and homocysteine levels. And you'll see all these patients with, we worry about creatinine. We measure it for kidney failure, right? So if someone's kidneys aren't working, creatinine builds up. But the bigger problem is low creatinine, because it's a big indicator of muscle wasting, right? It means that people don't have enough. So creatinine, so there's these interesting biomarkers that we've been using for 100 years, it feels like, right? And if you can get them right, they're very, very powerful at saying, you know what, my systems are working properly, right? And part of the goal is to remove some of the health anxiety, right? This feeling of health is that you just don't know, am I going to walk down the street, get hit by a bolt of lightning, like something's going to hit me completely out in left field. And what we've learned from the prodrome analysis of diseases and understanding the key deviations is that, look, you can't remove all possible risk factors in life for sure, but you can get rid of a lot. Like you can look at a whole lot of systems, and they're relatively straightforward to restore to normality. And then you can kind of live your life a little bit, check up on them a little bit, right? And like once you know your car isn't leaking oil, you don't need to check oil every single week. Like you, at some point in time, you say, okay, you know what, I'm comfortable. I'm going to check it every 1,000 miles or whatever it is, right? And you should get that way with your health. Like especially the core systems, right?
Yeah.
And then you want to check every now and then in case something happened to you in the intervening time, because stuff happens, right? You'll get an infection, you'll get something in your life, and so keep an eye on it. But part of this whole deviation from health model is about relieving some health anxiety and improving performance, because then people can then they can focus on optimizing and pushing their performance to the next level, right? Because you can't push your performance to the next level if a core system is not working, right?
Yeah, I like what you said about mitochondria, because if you had a big whiteboard and you wrote down every disorder known to man, what do they have in common? Well, the plasmalogen issue, but mitochondrial issues. So plasmalogens are kind of like the new mitochondrial insufficiency in a way.
Yeah, well, it's on your membranes, right? Your
Yeah.
body has, like, so look, your body has 100 trillion mitochondria, because every single cell of your body is going to have multiple mitochondria. But you have 30 trillion cells. Every single one of those cells has a biological membrane encasing it, which is a phospholipid bilayer. And inside those cells, all the internal organelles are divided and differentiated by their membrane structure. So your membrane structure is what makes you not have soup. Like your body has physical structure, it separates things. So it's a core physiological construct of human biology. The mitochondria drives all your energy. So anyone who has energy issues, absolutely, it's mitochondrial. It's a good example. What happens when you get the flu? People they get muscle pain and they feel tired. Well, you know what the flu does? It causes inflammation, okay? And your body is now fighting this bug that you have, right? And it's created a mitochondrial load on your body. It's like you're driving your car and all of a sudden someone put a piano on top of it. And you're wondering, why is my car driving so sluggishly? Like I can't, every time I try to go up a hill, my car goes slow. Well, it's because it's carrying a piano. And so and that's your mitochondrial capacity. And so whenever anyone feels tired, it's because their mitochondrial capacity is not working properly. And then, and so, yeah, it's such a core component of everything, and it drives our risk of cancer. It drives our risk of a lot of things. As we age, type 2 diabetes, these issues that we have, they're all related to this impaired cellular energy balance. So yeah, it's a core system. All the oxidative stress of your body ultimately comes from dysfunctional mitochondria, all of it.
And you mentioned the fact that the microglia are activated because the membrane there is lipid peroxidation, correct? And so anything like a stealth virus, a neurotropic virus, mold could lead to membrane oxidation. So you want to work on the membrane, but also remove the stressors.
Correct. So when you get inflamed, when you get an inflammation event for whatever reason, like you just mentioned, a mold or whatever it is, what happens is that inflammatory system outside your cells, the actual mechanism, it pumps a bunch of glutamate on your cells. Okay, and glutamate is a excitotoxic molecule. It goes into your cells, but it actually acts like glucose. So when a cell takes in glutamate, it basically says, okay, I'm going to process glutamate. I can't process glucose, which is why all type 2 diabetes, insulin sensitivity issues are really driven by an component to it. Anyways, that goes into your cells. And so all of a sudden your cell it's getting pumped with both glucose and glutamate, okay? And it's putting an extra load on the system. And the mitochondria, its job is to take this energy, glucose or glutamate or fatty acids, and it burns it with oxygen, right? You breathe in oxygen and it's going to burn it into carbon dioxide and water. And if that cell gets overwhelmed, the mitochondria gets overwhelmed, it starts burning dirty. It's like smoke coming out the back of a bad car. The oil and the gas and oxygen mixture is off. And so that stuff, and the cell then tries to save itself. So it can't burn this, it can't process this information. And the smoke that the mitochondria have is called reactive oxygen species, typically superoxide anion or hydrogen peroxide. And the cell is going to try to save itself. Okay, so because it's important to maintain the integrity. So it starts spitting this stuff out, and it spits it out there's actually enzymes called these NOx enzymes, and they'll spit these electrons out, and then they get them out of your cell. And so now they're outside your cell, and then you have enzymes, you have a bunch of backup mechanisms, like your body has superoxidase mutase enzymes, it has catalase enzymes, it has glutathione, it has a whole bunch of backup plans, right? Because you have oxidative stress all the time happening. But if it's too much, all those backup plans get overwhelmed. Okay, and if it can't, at some point it overwhelms that backup plan, and that stuff that's spitting out of the cells starts peroxidating the membranes. And then as soon as that happens, it's the microglia that gets activated. And I tell people it's the cells of your body are like the houses in your neighborhood, right? You really don't know what's going on in any of your neighbor's house until a chair starts flying out a window and lands on the front lawn. Go, holy crap, something's going on. The Joneses over there. And that's what the microglia, and that's basically what happens in your cellular environment. At some point, that inside the cell, something goes wrong inside. And at some point, that whatever goes wrong on the inside comes out. And then once it comes out, it's like, okay, it's time to call the police. Something's going on over there. And that's your microglia coming back. And so, yeah, I think people, kind of chase their tails on certain things, but these systems are actually really, really well worked out, and you can solve a lot of these problems. And then after you restore that biochemical health, then you kind of got to repair. Like I think people confuse the restoration process with the repair and recovery process, because that's a bit more work, obviously, because now you got to clean up and rebuild from the damage. So
Yeah, I tell people the worst thing I can do for you is to just take away your symptoms and then send you on your way, because you're just one stressor away. You don't have enough of a physiological buffer zone. So you're one or two stressors away from being symptomatic again. And so I think you're spot on with that. What happens to plasmalogens during the cell danger response? Did they get spit out or chewed up, so to speak?
Well, the cell danger. So what happens when cells become dormant, right? So it's a maladaptation process. So plasmalogens will become, so often when a cell goes into a danger response, basically says, okay, I'm adapting to a dormant state, basically, right? And it's not functioning, so it shrinks. It kind of basically becomes like a spore, almost like a human spore. The membranes change from a fluid membrane to a more denser membrane. Okay, and some of the oxidative stress it'll selectively attack the polyunsaturates, which is the DHA molecules, and those are the molecules that provide the membrane fluidity. So as you selectively lose those omega-3s, the cell becomes a little more dormant, and it kind of will sit there. Okay, and then it's kind of and it trains itself to be antisocial, if you will, or withdrawn. And it's almost like a person who has had a bunch of negative social relationships, right? And they just said, I'm done with this. I'm not going out anymore. and so then you start waking the cells up when you activate them, and so then they don't trust their environment yet, right? They're still untrusting. And then as you wake them up, so sometimes when you wake these cells up, you wake up the death response. So you can actually wake them up enough that they'll die. And then you get these. And if that happens without the immune system around it, then that's when you get this senescent, excretion problem. But yeah, so plasmalogens themselves, we find that, so people with PANS, like people that have a really hypersensitivity situation, right? Then we need to go slower with them, because we kind of wake them up. There's a bit of it kind of wakes these cells up a little bit, allows your body to clear them. And so there's a bit more of a process there. So yeah, so that's kind of, they're not directly involved, other than the membrane structure is adjusted accordingly. That's the right word.
And are plasmalogens, are they incorporated into the mitochondrial membrane?
Oh yeah, they're in all the membranes. Yeah, so
Okay.
absolutely. So so they're critical they're in all the membranes of the body, and they're just different types. And so the intracellular membranes are actually even more important. So your outer membrane, what we call the plasma membrane, is a much more thick and robust structure. It contains a lot of cholesterol. It's about 50% cholesterol. People forget how important cholesterol is. And then your inside membranes, like of the mitochondria or your Golgi or your peroxisomes, those will have very small amounts of cholesterol. And it's basically the difference between your outside walls, which are really strong, heavy walls, and your inside walls of your house, which have less structure. And so it's your inside walls that are more fragile. And often they will get damaged first.
Sure. Yeah, I mean, that's super important, and that ties, two of the core systems you mentioned together. I use NT factor energy, it's a phospholipid complex, to help Garth Nicholson's work repair mitochondrial membranes, but I'm going to start using plasmalogens for sure. And so I look forward to reading more about them. Were you one of the first? I know you said they were discovered in the 1920s, but are you one of the only scientists studying plasmalogens today in the
There's a
US?
lot now around the plasmalogen community is grown. I was the first to really patent and discover their association with a lot of diseases. And these plasmalogen deficiency mediated diseases of aging. Okay, so in fact, a patent on it as a disease in and of itself, so to speak. So that my contribution has been really in the dissemination of knowledge that these deficiencies are causing diseases. They're not an effect of a disease, but they're actually causing these diseases. And then the invention of bioavailable plasmalogen restoration molecules is the other part that I've contributed to science. But yeah, there's a huge amount of epidemiological data out there now on plasmalogens. And so that's been, and I've done a lot of academic research. I've donated millions of dollars to academic facilities to do these large, because a lot of the technology that we use is just not available in most facilities. So we've done large clinical trials, large epidemiological trials. We do a lot of them for free with big institutions, just so that people can get that information and we get other people. But yeah, so in terms of my role in the plasmalogen space is really this association. And then now we have the tools. So we have the tools to do the restoration. And now we're doing a whole bunch more clinical trial work. So for example, for brain restoration, so I did my own brain, I gave a lecture on anti-aging. So I was able to reverse 15 years of aging of my own brain using high-dose plasmalogens, phospholipids as well, a few other things. But my occipital lobes, my white matter improved, my volumes improved in my brain, my cortical thickness improved. And so these are very powerful things. And so now this is the kind of work we do now with these. We have a big charity in rare diseases. So all these children with leukodystrophies and RCDP, we donate to a lot of those organizations. And then we talk about how do we really restore health in multiple sclerosis and ALS, dementia, Parkinson's disease. So my research now is really on really nailing down the restorative capabilities, because people have assumed, it's kind of breaking these assumptions that we have limits in terms of brain restoration. And I think we're learning that neurogenesis is very doable now, and not in a crazy way, in an actual just straight up way. And so that's where my focus has been on, these diseases. And then obviously community medicine is another big passion of mine.
And I'm looking at your website right now, but you have several different products. It's not just one plasmalogen product, correct? There's
Right. So
prodrome
we have two new products. So prodrome glia is basically the concentrated breast milk molecule. It's omega-9. That's your protection molecule. Like that's your get out of the emergency room molecule. It's a very highly protective. It comes into your membranes. It restores myelination. We use it extensively in autism. And then we now have the enhanced version, which we call prodrome glia PC+. And so we take the omega-9 plasmalogen precursor, we mix it with an egg yolk oil extract. So we take fresh egg yolks and we extract them with 100% ethanol, get all the oil, all the lipids out of the egg yolk. And then we add some CoQ10, vitamin E, D3, K2 to it. And we've noticed with our rare disease, and especially with ALS and MS, this really makes a big difference. So that's kind of a supercharged omega-9 membrane enhancer. And that's for protective. That's basically to resolve inflammation, restore myelination. The juice, the performance, the one that jacks you up though, is the DHA plasmalogen, this omega-3 version. So that's the prodrome neural. And that's a much more complicated biosynthesis or chemistry program, because we get the DHA from an algae source, and then we purify it to extremely high levels, and then we attach it to the plasmalogen backbone. This is the one for neuromuscular performance. And if you're an athlete, this is the stuff that really improves your muscle memory, muscle recovery. It's primary for cognition and Parkinson's. That's the one that gets rid of your brain fog. That's the volume button. Like that one there, just you'll feel it. You'll feel your vision, your lights get brighter, and then so the neuro is the juice, if you will. And we typically give the omega-9 at night while your brain is rebuilding, and then the omega-3 in the morning. That'll keep you active during the day. And then the supercharged omega-3 is taking that omega. It's actually really interesting because when we mix the prodrome neuro with the egg yolk oil, we're actually creating DHA phosphocholine because the way it gets absorbed in the gut, we're using human biochemistry for it as our own tool mechanism. So when you eat a phosphocholine molecule, for example, that molecule that you eat is not the molecule that gets into your blood supply. Okay, it goes through phospholipase A2, and then it gets absorbed as a lyso. And as soon as it gets past the gut lumen, it gets reattached with the fatty acid. So by combining the phosphatidylcholine from eggs and the DHA that's in the prodrome neuro, when it gets absorbed, you're actually delivering DHA phosphatidylcholine through the system. It's pretty cool. And it's a very, very powerful product and the reason why we put it in an oil form like that is that if you take it on an empty stomach, it bypasses all the liver metabolism. It goes right onto your chylomicrons. And that's how it gets into your muscles and your brain. So we can do pharmacokinetics of how, because your body is actually designed to absorb these lipids first, which is pretty cool.
So you have people take them on an empty stomach?
Yeah.
Okay.
Typically, right? I try to most of my supplements, like when we do our large protocols with all the different supplements, I like to get most of them in the morning on an empty stomach. And some that we get, like N-acetylcysteines and carnitines, we'll take them during the day. Like we'll take them multiple times depending upon the disease state. And plasmalogens can get 2 to 3 times a day depending on the disease state, like for our rare diseases. But mostly for most people, neuro in the morning, glee at night. And if you take them on a bit of an empty stomach, you get the maximum absorption because you're trying to pulse these things in. And so when we're dealing with vitamins and nutrition, there obviously you want a proper food supply, absolutely. But those things give you kind of a slow absorption as they get digested through your stomach. When we want to actually drive B12 or want to drive peroxidine into your cells, okay, when we want to create a reserve capacity, you want those little pulses and getting those in, and most of them are really well absorbed for the most part. So if you take them on a semi-empty stomach, it's not truly empty when you take the egg yolk oil with the plasmalogens because you're getting some fat calories there. But it's certainly in a fasting keto-like state. Type thing.
And so do you also have a phosphatidylcholine complex by itself as a standalone?
Well, we will eventually, but we kind of just blend it with those two products right now.
Gotcha.
We're just trying to build up capacity right now. So.
What's your take on, I see the debate about omega-3 fatty acids and PUFAs and Ray Peat's work and how it can lead to lipofuscin buildup in the cell. Is it vitamin E and other antioxidants? Is that enough to prevent them from being oxidized?
Well, yeah, so they're any of the polyunsaturates. So what separates us from plants are fundamentally 2 fatty acids from a membrane perspective. It's either arachidonic acid, which is our omega-6 polyunsaturated, okay, we get from linoleic acid, or DHA, which is your omega-3, which we get from linolenic acid, alpha-linolenic acid. Your body can make it from there. Those are 2 essentials. The human body cannot make omega-3, the human body cannot make omega-6. We must get at least the precursors from our food supply. But those polyunsaturates are the ones that are oxidatively, they're susceptible to oxidative stress, right? And so, but the omega-3, the DHA, when it gets exposed, it actually creates anti-inflammatory resolvins and protectants. Okay, so when we do blood testing, so the prodrome scan test looks at the phospholipid composition. It looks at the different fatty acids on the phospholipids because when you have an inflammation event, your membranes release fatty acids from the phospholipids in a very specific way. It's an enzyme called phospholipase A2. and it releases a fatty acid from the SN2 position. Now, we can make a lot of arachidonic acid on demand very quickly, and cancers and all these things will have high levels. And so you want to have high levels of omega-3 in your diet, because you want to enrich your membranes with the DHA version. If you don't take high levels of omega-3 DHA, your body will make up the difference with arachidonic acid. So the only way to keep arachidonic acid levels down is fundamentally with DHA. And not EPA. Your body doesn't use a bunch of EPA. So EPA is, you can use it as a drug. It's like a PPAR agonist drug. But your membranes actually have the DHA molecule. So so in that regard, unless you're taking 10 grams of the stuff, no, like you can definitely take high doses of DHA. The studies are pretty consistently reproducible. That's a good thing for the most part. In children with autism or inflammatory diseases, I typically stay away from too much DHA, because young people can make a lot of it. I'm not concerned about the oxidative stress of DHA, but it can be a bit stimulatory. So ADHD, autism, so it's a double-edged sword. It's anti-inflammatory, okay, but it's also stimulatory. So when you're trying to calm a system down, omega-9s are much more calming than omega-3s. So just use them back and forth a little carefully. So after you've kind of calmed the inflammation down a little bit, then you can, so it's kind of it's not a perfect black and white situation.
I remember back in the day, say 15 years ago, the general thought, at least amongst clinicians, was EPA works more systemically on inflammation and DHA is more for the brain. But what you just said says that that's not really the case.
No, so EPA is a metabolic byproduct of DHA. If you measure the membranes in the human body, you'll find there's extremely low levels of EPA. Your body does not put EPA in any of its membranes, okay? But it is a fatty acid, and it is a polyunsaturated, it's an omega-3 fatty acid. So it will get metabolized by peroxisomes. So one of the reasons why when people take DHA and they get a triglyceride lowering effect from DHA, the triglyceride lowering effect of DHA or EPA, basically it acts like a fibrate, basically. It acts like a PPAR agonist. It stimulates peroxisomal function, okay? And it has a drug-like activity, because those cells, and this is where people take the odd chain, like when we talk about C15, C17, okay, and they're saying, and that's a big fad right now, because those molecules are metabolized by a very specific peroxisomal enzyme called alpha oxidase. And by ingesting them, it stimulates the peroxisomes to be proliferated. And when peroxisomes are active, they metabolize fatty acids, and they're active when exercise. And so sometimes these like the glitazones, for example, they used to call them, the nickname was the exercise in a pill type of thing. And so what they would do is they would stimulate peroxisomal function, but the problem is that they have these myopathy side effects. Like they could never really get the drugs to titrate properly, which is why, so EPA, okay, is a PPAR agonist. So it'll stimulate peroxisomal function, it'll lower triglycerides. And so it is physiological active in that regard, but it's not an actual, you get this, you're better off to take more DHA, because your body cannot convert EPA into DHA. Your body can convert DHA into EPA. Okay, so if you take DHA, you'll never be EPA deficient. Okay, so your body it'll break it into that. And in fact, we measure on our blood test, you can measure the DHA to EPA ratio as an indicator of peroxisomal hyperactivity. So people with a mitochondrial dysfunction, okay, so when the mitochondria are dysfunctional, it can't do its job properly, which is metabolizing fatty acids. So all of a sudden, a bunch of these fatty acids go into your peroxisomes, so it jacks your peroxisomes up. And so you see this in autism and in multiple sclerosis patients, for example. And all of a sudden, your EPA levels go way up, and it's a very big indicator that you have peroxisomal hyperactivity. So these are things like, so the biochemistry of the human body, and so we've designed this blood test that kind of looks at all these things from a 30,000-foot view, and you can get a sense of that stuff. So I know it's a long answer to your question. So it's not like EPA is bad for you, but your body can't actually use it. You're actually taking a drug more than more than a nutrient.
Absolutely. Well, thank you so much for that thorough answer. What's something, I mean, you've been doing this research for what, 20 years?
Yeah, 30 years now. I'm getting old. So
Well, hey, you're aging in reverse, so I mean,
trying
it's all
to.
good.
It's fun. Hey, and no harm in trying, right? So
Hey,
that's the fun part.
that's right. And there was one study. So this guy on Instagram was talking about this study. I think it was like a one-off study that said DHA can increase cholesterol levels. That sounds like some big pharma propaganda. Do you know anything about that?
Well, if it can, that's great. It should. So we have a problem with chronic low cholesterol. So what DHA will do, okay, is it improves reverse cholesterol transport. So physiologically, so part of the reverse cholesterol transport system is there's two partners in a three-legged race regarding cholesterol transport. And people think of these two molecules, like we have HDL and LDL in the periphery, and we have just ApoE in the brain. So, but let's talk about the periphery, for example, for cholesterol transport. So you have two molecules, LDL cholesterol, which is your body's delivery mechanism. Your cells actually absorb the LDL particle and digest it and release cholesterol. So it's a way of cholesterol coming into your cells. Your HDL particles do not enter your cells. They stay on the outside of your cells, and it's called your reverse cholesterol transport. And so between the two of those systems, your cells maintain their optimal cholesterol levels in their membranes. And so when your body wants to get rid of, so when your cells are happy and full, okay, they export cholesterol, and they export it through the HDL system. So what happens then is that DHA plasmalogens are part of it. They improve reverse cholesterol esterification and removal. Then the phosphatidylcholine system takes that cholesterol, esterifies it, and puts it on an HDL particle and sends it back. Okay. So when you take DHA, you can stimulate reverse cholesterol transport. Second thing is that most of the cholesterol, every single cell of your body makes cholesterol. And so when your cholesterol level, and it makes it from peroxisomes. So your peroxisome does its beta oxidation step, and the acetyl-CoA created from that is used to make cholesterol. And so for the most part, if DHA increases your cholesterol level, it's probably a good thing, because people have, so if you're interested in longevity, if your viewers are saying, hey, what are the biomarkers that will indicate that I'll live the longest? Total cholesterol should be between 220 and 240. Okay. So anyone who tells you want to get your cholesterol low, okay, it doesn't want you to live long. Because soon as total cholesterol levels gets under 200, all-cause mortality starts going up. LDL cholesterol should be always over 120. Okay, soon as LDL cholesterol gets under 120, okay, your all-cause mortality goes up. HDL is the opposite. Okay, you want it above 50, ideally in that 60 to 70 range, okay, but as soon as it gets under 50. So that's what you're saying, what you can see very clearly here is that when your cells are sick, a big indicator of sickness is low cholesterol. If you have cancer, say you get diagnosed with cancer tomorrow, go to your doctor, say, oh my God, I've got cancer. The level of cholesterol in your blood will predict how well your prognosis of chemotherapy. If you have low cholesterol, you have a less likelihood of surviving cancer than if you have high cholesterol. These are actual straight up facts. Okay, yeah. The all-cause mortality data, that's in 162 countries. Okay, that is not a one-of study. We're talking tens of millions of patients data points, and so it is not even remotely up for conversation. Now, what you are concerned about is C-reactive protein and oxidized cholesterol. But it's not oxidized cholesterol either, people. This is another total fallacy. What happens with oxidized LDL, it's never the cholesterol that gets oxidized. It's actually arachidonic acid on phosphatidylcholine that drives C-reactive protein levels. So these are facts. These are not even remotely up for conversational. And this stuff has been these are huge studies over and over, even big New England Journal of Medicine papers showing that the cholesterol lowering statins only had a benefit in people with high CRPs. with high LDL and high CRPs. And there's a long story to talk about. This history goes way back to familial hypercholesterolemia, when people were trying, this whole story about cholesterol lowering all came from people with an LDL receptor mutation, that they can't absorb LDL in the liver, so their LDL levels go through the roof. And those people do get atherosclerosis, but that's not the rest of us. That's one in like, I don't know, one in 700 or something. And then it's like 1 in a million that gets a double knockout. It's a very small number of people. But anyways, like the history of these things and the linear process that some of these stories, and they don't rewrite the books once they get the new data. Okay, like you get an initial study and it gets stuck, and then when it gets debunked, nobody rewrites it. It's quite disturbing. So anyway,
Like you said,
sorry to get on a soapbox on that one. So back to your question. If typically speaking, if DHA increases your cholesterol levels, that's probably a good thing. You probably had unhealthy low levels.
I have to write a letter to this company that I use that it's called Sonic Cholesterol. It takes 1 egg's content of cholesterol, puts it in a capsule. A lot of the kids on the spectrum I've worked with and people with chronic issues have low cholesterol, but it's been so demonized to have to write a letter and prove it. You know, it's like you're ordering an illicit drug or something. But I know Daniel Amen, he said when he worked in the prison system, the prisoners with the most violent histories and with the most violent outbursts had the lowest cholesterol levels.
Yeah, low cholesterol typically means poor mitochondrial function. And when you have, because it's a very, like, if you see people with well, typically low cholesterol is yeah, it's definitely associated with aberrant psychiatric behavior. Absolutely, 100%.
What's something that you know today you wish you would have known 10 to 12 years ago?
It's kind of funny, like that question, things are kind of just a linear process. So I don't even know what I didn't know then anymore. I think probably just the realization of how difficult it is to change the status quo in medicine, right? And being a bit more patient, like realizing, but a lot of these programs I've put in long-term plans for these things, right? Like we do DNA serine separation because it's important for ALS and other things. And like I invented that technology in '94. And so
You said it's D and L serine?
yeah, so D-serine is a coagonist for the NMDA receptor. And so it's driven in all the excitotoxicity issues of the brain, but it also drives our neurodevelopment. But anyways, it's an important biomarker to be tracking. But I guess really it's I don't know, because I don't know what I don't know tomorrow, because I'm always learning how much I don't know. Like it's tomorrow is another day of learning that and so I just dig. To me, every life is just one constant pulling on a string and seeing where it takes me. And so I don't kind of there's really the revelation of like this health versus disease. Yeah, it would have been nice if I knew that before, or plasmalogens. But I kind of found them out in a natural progression of time. So I don't even know so the things that I know now that I didn't know then, I don't think I would have been able to use that information back then.
Right.
Right. And so part of that is like, I find that most of the time the knowledge that I gain, because I'm always digging into things, I find the universe, basically, I know it sounds goofy, but the universe typically provides. It's like when I'm ready to find something, it kind of comes to me because I'm just out there working and figuring out, just plugging along, skin to my knees every now and then, getting up again, and just kind of being in the mix of things. And yeah, because the stuff that I know, like how to run, the MRI technology, I wouldn't be able to use it 20 years ago.
Right.
And so it's kind of, I can only take in so much at a time. So there's kind of, so that's kind of, for me, it's a kind of, that's kind of, I know it's an interesting question. It's, but
Yeah.
I don't know if Yeah, I would like to know all this stuff back then. I would have been able to save myself some time, but I don't know if I would have been able to use any of it. So
Right. Well, you're doing amazing work. Keep it up. Thank you for the work that you're doing. Hopefully we can have you back on for an update in the future. We're going to put all your links up in the show notes so people can find you and find your products. And I highly encourage people to read more about the plasmalogens. I'm going to definitely buy some for
yeah,
myself.
the book Breaking Alzheimer's really digs into it. It really shows a huge amount of data in that book, and it goes through the role of plasmalogens in Alzheimer's disease, but also in aging, all-cause mortality, the ApoE4 genotype and its risk factors. So anyone's it's an interesting book on just how the brain works, and certainly performance. People that are interested in how the acetylcholine system really drives your cognitive performance. It really drives your neuromuscular performance. So if you're an athlete or if you're just interested in high performance, that book is really a roadmap of understanding some of these core systems. And then from there, you can kind of go deeper down the rabbit hole as you wish.
Absolutely. Yeah. And acetylcholine is needed to activate the vagus nerve.
Absolutely.
So,
Yeah, and the whole barrel reflex sequence is all driven by there. And so that's another. So then people take these beta blockers, right? They're blocking a noradrenaline, the noradrenergic response, which is the yin and the yang to the vagus acetylcholine response. And so really just improving acetylcholine gets rid of your need for the beta blockers. And so it's kind of yeah. So that's a perfect example of how adding a positive is much better than trying to block a negative.
yeah.
Like if you can add a positive to the system, which is improving vagus nerve stimulation, okay, then you don't need to block the negative because
Right.
the system balances itself out.
Right. Well, thank you so much for your time. Hopefully we can have you back on in the future.
Absolutely.
And I hope you have a blessed day.
Thank you very much, Tim. Really liked it.